Welcome to the third video in the quantifying chemical compounds unit. We are going to be using the concept of molar masses and using them in calculations. This calculations really similar to those that we completed in the moles section of the atomic structure unit. So we are basically going to be doing the same thing that we did in the moles unit of the atomic structure unit, but instead of molar masses of single elements, we're going to be using the molar masses of compounds like what we calculated in the last video. Just as a heads up, our answers are going to have the same number of significant figures as our given, so I hope you have not forgotten how to determine the number of sig figs. So let's say I gave you an example that looked like this. Determine the mass of 48.6 moles of sodium chloride. If I gave you an example that looked like this, a few things should be going on in your mind. One, you should remember that mass is actually calculated in units of grams. And two, sodium chloride would be better written as a formula. So let's start off with that. Now, maybe some of you guys know off the top of your head what sodium chloride is, but just in case it wasn't so easy of an ionic compound to determine the formula for, remember you have to find the charges first of each of the ions. Make sure you can add enough ions of each to cancel out the charges. So we see here that the charges add up to 0, and here's our final formula for sodium chloride, NaCl. So back to the original problem. We can set up a dimensional analysis problem using GWR. Our given in the problem is 48.6 moles of NaCl. Our want is mass, but remember mass is measured in grams, so we want the mass of NaCl. And now it's time to find a ratio. Here's where you stop and think. What is the relationship between moles and grams? How are they related to each other? One thing that you should be thinking of always when you see mass from now on is think about the periodic table. What kind of information can the periodic table give you in terms of mass? Well, the ratio can be determined by calculating the molar mass like what you calculated in the last video. So whatever calculated molar mass of NaCl is equal to 1 mole. We're calculating how many grams are in 1 mole of NaCl, and then we're going to calculate the grams in 48.6 moles of NaCl. So what we can do to calculate the molar mass is to use our periodic table and to use our formula of NaCl to calculate the molar mass of NaCl. So sodium has a mass of 22.990 grams, chlorine has a mass of 35.453 grams, and these numbers here represent the number of atoms in the formula. We add them up. We round this value to the thousandths place, and we end up with 58.443 grams per mole. I'm going to take this unit and I'm going to write it as a ratio here, and here is my molar mass. So basically what this problem tells us so far is that I know that in 1 mole of NaCl there are 58.443 grams. So how many grams are in 48.6 moles? Essentially, that's what we're calculating. I know you can do some simple algebra to figure that out, but we want to use dimensional analysis because this is just the beginning. We're going to be dealing with super long problems through a method, through something called stoichiometry, and we want to be ready for that when we get there. So that's why we're learning dimensional analysis, to make that transition easier. With dimensional analysis, we start with the given over 1. The given not only has the number, but it also has a unit, it also has a substance, and I promise later on in the school year, having the substance there is going to be so helpful. Just practice doing everything perfect now so it makes it easier on you later. I see moles of NaCl in the given, so I know that diagonal from that, if I want my dimensional analysis to work, I'm going to have to use my what I see in the ratios and grab the unit, the number, and the substance and put that diagonal. So I have 1 mole of NaCl diagonal from 48.6 moles of NaCl because I need the units and a substance to match up diagonally. I take the other side of the ratio and I put it in the numerator, so 58.443 grams of NaCl goes in the numerator, and now I can calculate. I notice that I only have numbers in the numerator, but I'm going to go ahead and tell you the calculation out loud as if I had different numbers in the denominator. So in my calculator, I would type out 48.6 times 58.443 divided by 1, and rounded to 3 significant figures. Well, actually, the calculator value I get is 2,840.3298, but I need to round this value to 3 significant figures. So I start from the left. 1, 2, 3, there's my third significant figure, and I have to remember that in order to keep the value in the thousandths place, I have to retain that 0 and round it off as 2,840 grams. This number still has 3 significant figures, but by leaving the 0 and knocking off the decimal place, I still have a value in the thousandths place. So I do have another acceptable answer. This is just a normal carried out value, if you want to call it that. I can also represent this as a scientific notation value. So I wish I had put a little box around these two answers. I would accept these as correct answers. Either one of these would be fine. Now, when you get really good at dimensional analysis problems, I'll go ahead and tell you this stuff is not necessary, the GWR part. I'm doing that to help organize your thoughts for now, but then when you get really good, you can just get it down to this problem part, and I'm totally fine with you doing that on a test or quiz or on your scratch paper or your homework once you get it down. Here are the general tips for working with molar mass problems. If you have a G and a W in your problem and you notice mass is involved, whether you're talking about grams, kilograms, or milligrams, remember that you're going to determine your molar mass and you're going to use your periodic table to do so. Anytime you see the terms atoms, molecules, or formula units, we're going to use Avogadro's number. 1 mole is equal to 6.02 times 10 to the 23, and then depending on what substance X is, we can insert the term atoms, molecules, or formula units. They're all really similar to each other. It just depends on what substance X here actually represents. And finally, if you see two different substances in the given and in the want, like if you saw carbon dioxide versus oxygen, we're going to have to do a little bit more thinking. I'll talk more about this when we get to that specific practice problem, but let's go ahead and look at the next example. Let's say you are being asked to determine the number of moles in 582 grams of magnesium nitrate. The first thing I want to do is I want to go ahead and take that magnesium nitrate and write a formula out of that. So I recognize this to be an ionic compound, and with an ionic compound, I have to consider the charges first. According to the position of magnesium on the periodic table, magnesium has a 2+ charge. Next, I need to find the ion for nitrate. Nitrate is a polyatomic ion, and it can be found on the back of your periodic table. And so when you look for nitrate, we find the formula to be NO3 with a -1 charge. Just looking at these two ions, you might recognize that you would need 2 nitrate ions to cancel out with the 1 magnesium ion, since we have a +2 charge versus a -1 charge. Or you can apply the crisscross method in this case, and you end up with a formula that looks like this. Mg inside of your parentheses, NO3, and then a 2 on the outside of the parentheses. Here's our formula for magnesium nitrate. Let's go back to the problem and set up our G and W now that we know what the formula is for magnesium nitrate. We have 582 grams of magnesium nitrate as a given. We're looking for the number of moles, and we have to stop and think. What is the ratio? What is the relationship between the given and the want? How are grams related to moles? So I know that grams and moles are related through a molar mass. A molar mass is what you learned in the last video, and that's where we take the masses from the periodic table for magnesium, for nitrogen, and for oxygen, and we multiply it by the number of atoms of each, and we add up those numbers. Here we have a calculation for just 1 magnesium atom. So if you look at magnesium on the periodic table, you will see that it has a mass of 24.305 grams, and we only have 1 magnesium in the formula. We have 2 nitrogens in the formula. That is indicated by the 2 on the outside of the parentheses. The mass, according to our periodic table, is 14.007 grams. So that's how I end up with the 28.014. 2 atoms of nitrogen times the mass times 2. And we have 6 oxygens in the formula, not 5. We have 6, 3 times 2 here. So 6 times 15.999. This is our mass for oxygen. We add these all up together to calculate what is called the molar mass. While grams per mole is the correct unit for molar mass, I'm going to take this unit and show it as a ratio. For every 1 mole of magnesium nitrate, there are 148.313 grams of magnesium nitrate. So let's take that ratio and put it in our relationship or our ratio part of our GWR problem. So let's start the problem, because I don't see any terms of atoms, molecules, or formula units, so we don't need Avogadro's number in this problem. We'll start off with the given over 1. We will find the unit of grams and place it diagonal from the given. And so as we scan our ratios, I see the unit grams. We'll put that in the denominator. Let's put the other side of the ratio in the top, because that's how dimensional analysis works. And we can go ahead and calculate. In our calculators, we can type in 582 divided by 148.313, and we get 3.924. Remember, with dimensional analysis, we will multiply by any numbers in the numerator and divide by any numbers in the denominator. So let's say these were different numbers. Let me just say out loud how I would calculate that. 582 times 1 divided by 148.313. So I have this number that I calculated. This is a calculator value, but according to the given, I have to round it to 3 sig figs. So 1, 2, 3. I look at the 2 and the number next to it. I decide, does this stay at 2 or does it round up to a 3? And it stays at 2, so I'm going to finish off my answer with 3 significant figures as 3.92 moles, because that's the unit here, of magnesium nitrate. Next example, determine the number of molecules in 47.3 grams of sulfuric acid. I do not have a formula for sulfuric acid given to me in this problem, but I might memorize the formula for it, or I can remember that if you ate something icky, you might get the itis. So sulfuric must have been formed from sulfate, and the formula for sulfuric acid is H2SO4. Here's our given, 47.3 grams of H2SO4. We are going to calculate the number of molecules of H2SO4, and we stop and think. What is the relationship between grams and molecules? Well, first off, we didn't really talk about the direct relationship between grams and molecules, although you might have come up with one just based off of some other ratios we've used, but here are some general rules. Ask yourself, do I see the terms atoms, molecules, or formula units involved? Anytime you see one of those keywords, atoms, molecules, or formula units, you will be using this ratio. 1 mole of that substance equals 6.02 times 10 to the 23, whatever unit matches up the substance, and in this case we're using the term molecules. Now I abbreviate molecules as MC. It's a lot shorter than writing molecules, and never abbreviate molecules as MOL or MOLE, because that means moles. So that was our first question for coming up with the ratios. Do you see the words atoms, molecules, or formula units? And we do, so write this ratio down. The next question we ask ourselves is, do we see mass involved in any way? Grams, kilograms, milligrams? And we do. So since we see mass involved, that tells us, hey, calculate a molar mass. Calculate the molar mass for H2SO4. So here I have a generic ratio for molar mass, and I'm going to stop and try to calculate this molar mass now. In the formula, I see 2 hydrogens, 1 sulfur, 4 oxygens. The 4 does not go to the sulfur. I don't see parentheses. It just goes to the oxygen. So 2 hydrogen, 1 sulfur, 4 oxygens. When I calculate that, I end up with 98.078 grams. This is the molar mass of H2SO4. So those are my two ratios involved, and let's go ahead and get started with the dimensional analysis. We always start with the given over 1. After the given over 1, we're going to use the units in the given to drive the rest of our problem. If I see grams of H2SO4 in the given, well, I need grams of H2SO4 diagonal from that. So I scan all of my ratios, and I notice one of my ratios has grams of H2SO4. So I'll take this entire value, put it diagonal from the given, and then I will put the other side of the ratio above it. So just as a double check, grams of H2SO4, grams of H2SO4, check. I can move on with the problem. For the next part of the problem, I know I'm going to have two steps here because I have two ratios, and I've already used this ratio up. So some people like to put a little check mark. You can do that too if you want to, if it helps you to remember not to use it again. But I know that I haven't used up this ratio, so I'm going to look at my moles of H2SO4, cancel it out with the moles of H2SO4 on the bottom, put my Avogadro's number at the top, and I could abbreviate that as MC. And now I know I'm done with my problem. All I have to do is calculate. So this is what I'm going to type into my calculator. Actually, I'm going to give you two different options here. Here's your first option. You can type in 47.3 divided by 98.078 times 6.02. Hit that EE or EXP button on your calculator, then 23, and you hit enter. You should get a number that looks something like this, rounded to 3 significant figures. Your calculator is not large enough to carry out 23 digits, so you should only see a scientific notation value there. Here's the other way you can type in this problem into your calculator. 47.3 times 6.02. Hit that EE button for the times 10 to the exponent section. So again, 47.3 times 6.02 EE, 23, divided by 98.078. I skipped all of these ones because they're not going to make a difference in my calculation, and you still should get the same exact answer. Here is our last example, and this example is really different from the other ones. So if you feel pretty comfortable with 1 through 3, don't stop watching because this is a little bit different. Now, in the problem, it's asking us to determine the number of ions of oxide in 3.6 moles of TiO2. So my given is 3.6 moles of TiO2, that's the only number given to us, and the want here is ions of oxide. If you look really closely at the given and the want, these are two different things, the TiO2 versus the oxide, so we have to think a little bit about our ratios. According to the number of oxide ions in just TiO2 in general, there are 2 ions of oxide. See, there are 2 ions of oxide in one formula unit of TiO2. You have to watch out for your vocabulary. This is where the first video is going to be kind of helpful to make sure you know the difference between, or the relationships rather, between ions, formula units, moles, molecules, all of that business. So a formula unit is something teeny tiny, and ions are also teeny tiny. So for every one formula unit of TiO2, there are 2 ions of oxide, which is O2 minus. I also have to consider the idea that since the given is moles, I need the relationship of Avogadro's number. In 1 mole of TiO2, there are 6.02 times 10 to the 23 formula units of TiO2. This ratio was necessary because at this point, if I was trying to get from ions to moles with just this ratio, all I could calculate is from ions to formula units, and I didn't have enough information to get to moles. So this ratio will help me convert from formula units to moles. These two ratios are the only ones that you need, but I will admit it is a little difficult to think your way through getting both of these ratios and understanding the difference between a formula unit, ion, mole, and so on. So if you need to, go back and watch that first video and see if you can figure out that relationship a little bit better now that you know a little bit more. Alright, so let's start the problem like we always do. Here's the given over 1. We find moles of TiO2. Right over here, let's put that diagonal from the given. Let's take the other side of the ratio, put it on top. Let's take this unit of formula units of TiO2 and cancel it out diagonally with this other formula unit of TiO2. 2 ions of oxide go in the top. And now we can calculate. There are a bunch of 1s in the denominator, so in your calculator, you're just typing in 3.6 times 6.02 EE23 times 2. This is the answer you get, and this calculator answer also will not fit in your calculator, so you will always see it, you will only see it as a scientific notation. I've also rounded it to 2 significant figures, 4.3, because our given has 2 significant figures. Now, one thing I'm going to mention is over here, when I say EE, I'm saying EE, but only press that button once. It's just because the button is called the EE button. So that's the 4th example. If you're feeling pretty confident, I would say go ahead and try to do your homework now. Your homework, I believe, is set 2, and if you're not feeling kind of confident, let's go ahead and keep working on that practice box that you guys have in your notes. So here are the 3 practice box problems. If you want to start off by practicing them first and then coming back and watching the videos to make sure you did them right, that's fine with me. Or if you want to just keep watching to get a better idea, then you can do that too. But just in case, here are the answers for the practice box, but it's not about the answer. It's about making sure you can get there. So even if you know the answers right off the bat, you should still try out the problems and make sure you can get those answers. That's why I always like to give calculation problem answers out from the beginning, because then like when you finish the problem, you can tell right away if you did it right or not without having to wait for me to go through the entire problem. So here is the entire practice box question 1. If you're going to determine the mass of 9.45 moles of dinitrogen trioxide, it might be worth knowing that the formula for dinitrogen trioxide is N2O3. Here is our given, 9.45 moles of N2O3. We want to determine the mass, which means calculate the grams of N2O3, and we want to ask ourselves a few questions. Question 1, do you see atoms, molecules, or formula units? No, we do not, so we do not need Avogadro's number in any way, shape, or form. Second question, do we see mass involved? Yes, we do. And because we see mass involved, calculate the molar mass of the substance, N2O3. So this is the same substance. We know there's nothing too difficult about this problem if you know the basics. And here is our ratio that we just calculated. 1 mole of N2O3 equals 76.011 grams of N2O3. And this number was calculated using the periodic table, finding the mass of nitrogen, multiplying that by 2, and then adding it to the mass of oxygen times 3. This problem needs no more ratios. We can get from moles to grams just through this ratio here, moles to grams. So let's start the problem with the given over 1. Moles need to cancel out with moles, so let's take this portion of the ratio and put it diagonal from the given. I'll take this part of the ratio and put it on top, and multiply across and round your answer to 3 significant figures, and we get 718 grams of N2O3. For the second example, we're determining the mass in kilograms. This is a little red flag here, so make sure that you realize we're going to calculate kilograms in this problem of 5.83 times 10 to the 23rd molecules of HCl. Our given is 5.83 times 10 to the 23rd molecules of HCl. We want the mass, but make sure you know it's in kilograms, and now we come up with our ratios. We will ask ourselves the same two questions we've been asking ourselves throughout this lesson. The first question is, do we see the term molecules? Yes, we do. And since we see the term molecules, we definitely need to write down Avogadro's number. Oh, I didn't want to show you all of those ratios all at once. All right, so this is the ratio with Avogadro's number. 1 mole of HCl equals 6.02 times 10 to the 23 molecules of HCl. The reason why we use the word molecules for HCl is because this actually does represent a molecule, not a formula unit, not atoms. So that's why we're using the term molecules. Next up, we want kilograms of HCl. So not only do we calculate the molar mass using the periodic table, because anytime we see mass, that's what we do, we also need this additional ratio of 1,000 grams equals 1 kilogram. Now we can start the problem. Given over 1. Molecules need to cancel out with molecules. As you scan the ratios, there are molecules right there. Take this, put it in the bottom. The other side of the ratio goes in the top. If you want to, put a little check mark there to say I've already used up that ratio. Don't use it again. Then we take this ratio because this says moles of HCl, we need the units and substance to cancel out diagonally, and we put the 36.461 grams at the top. Check off this ratio because we've used that one as well. Finally, let's go ahead and convert our grams into kilograms by putting our grams in the denominator, kilograms in the numerator, and now we are done. Make sure to hit pause and calculate this value. If you do not get the answer I'm about to reveal, then you need to rethink the way that you are typing things into the calculator. I've had several students in the past lay out their problems beautifully on paper, but then all of their calculated answers are wrong because they were typing things incorrectly. So let me tell you how you would type it in correctly. 5.83 EE23 divided by 6.02 times 10. 6.02 EE23 times 36.461 divided by 1,000. For every number in the numerator, you can multiply them. For every number in the denominator, make sure to hit the division sign between each value or use your parentheses. However you do it, you should get an answer that looks like this or this. Both of these answers are rounded to 3 significant figures, 1, 2, 3, 1, 2, 3, and remember the zeros in the front are not significant. Should you realize that you're not very good at significant figures, don't forget that our periodic tables actually have the rules on the back. So nice little cheat sheet there for you should you ever need it on a test quiz or even on your homework. Here's the third example. Determine the number of molecules in 782 grams of N2O3. So the given 782 grams of N2O3, we want molecules of N2O3. Let's ask ourselves the 2 magic questions. First question, do we see atoms, molecules, or formula units? Yes, we do. We see molecules. Therefore, we are going to use Avogadro's number as one of the ratios. Oh, there it is. We are going to use Avogadro's number as one of the ratios. And anytime we see grams or mass involved, which we do, we are going to calculate a molar mass. Now, you saw my animation was a little out of order there. I didn't mean to show that to you right away. But anytime you see mass, we need to calculate the molar mass. So in case you are not sure where this value came from, when I recognize mass is needed, I will use the periodic table and the mass of nitrogen, multiply that by 2, and then add it to the mass of oxygen, multiplied by 3. That's how I get 76.011. The problem can go ahead and move on with the given over 1. I have grams in the given, so I need grams diagonal from that. So let's take this portion of the ratio and put it in the bottom. Put this at the top. It's the other side of the ratio. Diagonal from that, I'll take this other ratio, because I've already used this one up. Don't use it again. Sometimes you might I've seen students accidentally use it over again, and you just go into this big whole loop thing. So 1 mole of N2O3 in the bottom, 6.02 times 10 to the 23 molecules in the top. Double check and make sure all of your units cancel out diagonally. They do. We're left with molecules of N2O3. Oh, good. We wanted molecules of N2O3. Now for your calculator. You can type in 782 times 6.02 EE23 divided by 76.011, and we get 6.19 times 10 to the 24 molecules of N2O3. This is rounded to 3 significant figures. Maybe you've noticed this, maybe you haven't, but anytime you have a number dealing with atoms, molecules, or formula units, you're going to have a huge number, something with an exponent in it, something with scientific notation, because molecules are so small, you need big numbers to represent those. And that's it.